Hey there, Calc kids. Today we're looking at good old 4.4. No video today. Kind of getting over a cold, so I'm gonna have to blow my nose periodically. So nobody wants to do that. Nobody wants to do that. Today we're gonna look at math, business, economics, industry, discrete phenomena with differential functions. Okay, we're gonna look at most of that. But we are going to get into the real life nitty gritty about what all this calculus we've been doing is about. Okay? Well, let's just jump into it. I will give you a printout with these on it. Please remind me to. Solving Maxmin problems can always be done with 6 simple steps. First thing we should always do is understand what it's asking. Read it carefully and write down what we're trying to find. Okay. Next, we need to come up with a mathematical model of the problem. And some of my favorite ways to do this are by drawing pictures, bring in variables, write formulas. Okay. And if we do those things, we will be able to solve any sort of Maxmin problem. Graph it, graph the function. Find its domain, range, see if there's any weird things happening to it, see if there's a mountain climber, all that good stuff. As always, find the critical points and endpoints, because those are going to be either a max or a min, or not, could be an inflection point. And solve the model. If not sure, try again, look back at it, make sure you're right. And 6, interpret, see if it makes sense, put it into the situation in which the original question arose. AKA label your units, see if it makes sense, all that good stuff. Okay? 6 steps to success. Max profit. Max profit occurs at the production level at which marginal revenue equals marginal cost, aka your derivative of your revenue equals your derivative of your cost. Now think about this. If profit is the amount of money coming in minus your cost, then it makes sense that well, think about this. If you find the derivative of this whole thing, and usually to find where your max is, you set your derivative equals 0. Well, if you set this to 0, you can see where this formula arose from. Okay. Again, add your cost over, and you get where cost equals revenue. Your marginal cost equals your marginal revenue is where your profit is the best, where you get the most money in your pocket. Here's a graph saying the same thing. Max loss, ooh, no one wants that, as actually occurs at the same spot. So that's why we have to make sure we use the max, not the min. Gabish? Alright, suppose our revenue is coming at 9 times x, our units produced, and the cost is x cubed minus 6x squared plus 15x, where x represents thousands of units. Where are we maximizing a profit? Okay. So what we do is, I do this a little bit differently in the book. What I'm going to do is find my profit. My profit is always going to be my revenue minus cost, right? Right. So my revenue is 9x minus my cost, which is x cubed minus 6x squared plus 15x. Okay. Distribute that negative through, and we get what? 9x minus x cubed plus 6x squared minus 15x. So really, our profit function is negative x to the third plus 6x squared minus 6x, right? Right. Give you guys a second. Now what we do is set that equal to 0. I'm sorry. We take our derivative, which would be negative 3x squared plus 12x minus 6. We take this and we set it equal to 0. Okay. Now I'm going to factor out a negative 3. When I do that, I get x squared minus 4x plus 2. I factor out a negative 3 because I like having a positive in front of my x squared. It tends to make my life a lot easier. Okay? Okay. So negative 3 gets canceled, and we're left with this, which is not factorable, so we still have to use our quadratic equation. So we quadratic this, it means our negative b plus or minus the square root of b squared minus 4ac all over 2a. When you do that, you get 4 plus or minus square root of 16 minus 8, which is 8 all over 2, which if you simplify that even more, you get 2 plus or minus root 2. Okay, so we get two answers. 2 plus square root 2 and 2 minus root 2. Well, according to our graph, the 2 plus root 2 is going to be the max for profit. Okay, and if you look at your graph, it'll actually look a little bit differently. Yours will actually look like this. Okay, and this will end up being the max at root 2 plus root 2. And this will be the min at 2 minus root 2. Okay, that's what yours will look like. Because we used profit instead of the two graphs on the same line. Okay, so when we do that, one second. So at this is going to be our max. Okay, and according to my calculations, this actually comes out to about 3.414. So it'd actually be about 3,414 units made. Okay. Okay. So let's do another one. Minimize cost. You just find out when your marginal cost is 0. Okay. Okay. Or I should say, you say equals 0 and you find the min. Because it could be a max. You could get a graph that looks like this and you find, you're like, oh, that's it. No, that's the max, not the min. Suppose you are just a good old fat fence maker. And you want to make a playground, or you want to fence in a playground because you want to put your kids free range. Allow them outside, put them in a fence. You want to find the yard with the largest area to make with 500 square feet of fence. Okay. So, first, let's go through those steps from before. Understand the problem. Okay. Identify. So when I understand this problem, I'm looking for largest area. I'm going to call A of x. Okay. So we're going to be looking for max on our area formula. Okay. 2. Develop a model. Okay. So we're making a rectangular playground where one side is length and the other side is width, right? Now, some things I know. I have 500 feet of fence, right? And I'm going to use that to make my perimeter. Perimeter of a rectangle is 2 times your width plus 2 times your length. Okay? And I know my area function, or area of a rectangle, is length times width, right? No, that was not the time. Freestyle. Length times width. Okay. Oops, so let's look at our problems here. So now we need to make a function. We introduce variables. Now what we have to do is we're going to end up having to get a function in which we just have one variable, because when we take derivative we can't do it with lots of variables. Okay. So what we have to ask ourselves is, how can we get length times width to just one variable? Well, if I look at this equation up here, let's say I subtract 2w from both sides. So I get 500 minus 2w equals 2l. And let's say I divide everything by 2, because I can. I get 250 minus w equals l. Now I can take this and plug it in wherever I see an L on my area formula. When I do that, I end up with an equation which is just in one variable, which is good, because now that I have an equation, I can find the derivative of that. In fact, I'm even going to go one step further. Okay. I'll pause for a second and graph this for you guys. Okay, so I did our next step and I graphed it according to our steps of success. I notice that it makes sense because I go from 0 to 250 on it. Now I have to find my critical points and endpoints. Well, my critical points, or I'm sorry, my endpoints, by the way, this is our graph again, from 0 to 50 goes. So my endpoints, oops, my endpoints, okay, are going to be from 0 to 250, right? And then my critical points are going to be where my derivative equals 0. So I find the derivative of my area A of x. Okay? And when I do that, I get what? 250 minus 2w. Okay? Derivative of this up here. And I take this and I set it equal to 0. And when I do that, I solve it. I get 250 equals 2w, so 125 equals my width. So my endpoints are 0 and 250, and 125 is where a critical point occurs. Okay. Okay. So I take a look at my steps to success. And I'm going to solve the model. Okay. Okay, well, looking at my graph, I can see 125 is going to be that max. You could also use your second derivative test. And if you take your second derivative, your a double prime of x, you end up with 2. Sorry, negative 2. So all we can have is a max on this. There's only maxes exist, okay? And since only maxes exist, there won't be a min, which makes sense because of this. So our second derivative is always negative, so there's only going to be maxes. The second derivative is negative, it's a max. Okay? So 125 is going to be our max for our width. So we take that, and we have an equation for length, which is 250 minus our width, which is 125. We get 125. So that tells me, and I'm going to do 5 and 6 together, I always do, that my width is going to be 125 feet. And my length is going to be 125 feet. So my max area is going to be length times width, which is 125 times 125, which is, let me check, 15,625 squared feet for that lovely playground. Okay, I gotta charge my pen for a second. I'm coming back though. Oh, my last problem, I swear. You want to make a rectangular box from a 10 by 18 centimeter piece of cardboard by cutting out congruent squares from the corners and folding up the sides. What are the dimensions with the largest volume you can make? What is that volume? So number one, what are we looking for? We're looking to maximize volume. By finding what length, width, and height, right? So 2, let's draw a picture. You have a 10 by 18 piece of cardboard, right? Okay, you're going to cut out squares from the corners in order to fold it up to make your box. Now, because these are squares, and we're going to they're going to be x by x, every single one. Okay, so when we look at this box, our height of this box is going to be x. Because if you cut these out and fold them up, you know, if you take a box, I'm going to fold up this side and this side. See, that's going to be the height of your box. Okay? Now, let's say this 10, or this is going to be our width. Now, this length of your box right here isn't going to be 10, is it? Because you're cutting an x out. Not just are you cutting this x out, you're cutting this x out as well. So your width is going to be 10 minus 2x. Now our length, well, it was originally 18, but again, if you looked at the dashed line, that's not going to be 18. It's going to be 18 minus x, and then minus x again, also known as 18 minus 2x. Okay? So if our volume is length times width times height, then it's actually, well, our length is what? Our length is our 10 minus 2x. our width is our 18 minus 2x, and our height is just x. Okay? So now we have the equation down into one variable. That should really be what second step is find the equation and get it down to one variable. Okay. Now, you gotta expand the sucker out. Trust me on it. When you expand this out, 10 times 18, 10 times -2, -2 times 18, you get what? 4x squared minus 36x minus 20x plus 180. I did that foiling, so this is actually negative 56x. Right? All this times x. So it's actually, hold on a second, it's actually 4x cubed minus 56x squared plus 180x. Again, full expanded out. We have to at this point in our life. So number 3 asks us to graph it. So I'll graph it, even though I'm not a fan. For some reason when I graphed it, it wouldn't let me move it lower than that point. When you look at this graph, you can see we probably go from 0 to about 5, because you can't have a negative height. This is in the twilight zone. And think about if x was bigger than 5, you'd be cutting off this whole side, which doesn't make sense. Okay? So that's my graph. So number 4, I'm pretty much going to solve it. So if my volume is this equation, right? Then my v prime is going to be, the derivative of it will be 12x squared minus 102x plus 180, right? I'm going to set that equal to 0, because that will give us our critical points. Our endpoints, like I said before, are 0 and 5, right? So now to find our critical point, first thing I would do is factor out 6. You do that, you get 2x squared minus 17x plus 30 equals 0. How did I factor out 6? I knew 6 went into 180 and 12, so I thought I'd try it, and it worked. Worked well. Okay. And when you factor this, 2x, x, well, negative 5 and negative 6 times 2 is negative 12 plus 5 is 17. If you don't see how I'm factoring this, you got to use your quadratic or some other method to solve it, okay? So that equals 0, right? Which means you set each piece equals 0. That means 6. And you plug in this one, you get 5 halves, also known as 2.5. So our solutions are 2.5 and 6. So when we plug in 6, if you want to try 6, if you plug in 6 to this equation, okay, you get a negative number, which means no dice, okay? Or you would get a negative number. Okay, so when you plug in 6, you get a negative number. So it's not 6, since we're looking for max. Okay? If you look at a graph, it looks like it's around 2.5. So 2.5 is our max. You could also find the second derivative. You get 24x minus 102. Okay? And when you plug in 2.5 into the second derivative, you get a negative, which means it's a max. Okay? And when you plug in 6, you'd gotten a positive, which means it's a min. So 2.5 is our max. the endpoints both give us 0 when we plug them in, or the points I made up. So, according to that, 2.5 is my max. So, we're going to do 5 and 6 now. That means my height is 2.5. My width, we said, was 10 minus 2x. 10 minus 2 times 2.5, right? So we get 5. And our length is going to be 18 minus 2x, or 2.22 times 2.5. So that's 13. Okay? So those are my dimensions. My height will be 2.5, width 5, length 13. So my volume will be, well, it's height times width times length. And when I multiply all those together, which I didn't do beforehand for some reason, so I'm going to do it right now, so bear with me. I'm going to do it in my head. Are you ready? I'm not doing it in my head, I'm cheating. Times 13. Oh man, I did it wrong. Oh man, I really did it wrong. 2.5 times 5 times 13. 162. 162.5. By the way, all these are in centimeters. You get 162.5 centimeters cubed since this volume. Long video. In fact, I think there's more. Well, I'm just kidding. Sorry about. Sometimes when you take college level courses, you gotta do a little bit extra work.